Hello and welcome to PMCD Maths Teaching, and this session we're looking at vectors. My name is Paul McDonough, and as I said on all these videos, it's primarily aimed at teachers perhaps the first time they've taught vectors, new teachers, but experienced teachers, you may find something interesting in here or useful for your own lessons which you can add on to it. Anyway, let's get into it. Rationale for teaching vectors in the approach that I'm using in this session. Okay, without repeating it too much, I mean, it drives me mad really a little bit that how are we supposed to get students enthused with this if it just seems like this, arrows on a page with some sort of algebraic, if it was to be done just as it was sometimes in a textbook and then for an exam, students would come out of this with really having no idea what vectors mean or what they're about, what they're used for. So the aim in this session really is to try and give them some sort of understanding of how perhaps these are used, and the uses for these are, very varied, as we know, through mechanics, computer programming, navigation, all sorts of things that can be used here. Okay, sequence of teaching, and see I've linked it to bearings. I've got a bearings video which actually links to this video as well. In this case, we're going to look at algebraic vectors and then column vector questions at the end, although we will talk about column vectors as we go through this. Okay, there's a lot of language in here as well, so it's good idea to get out the terms and referring back to these as we go through here. So we want to draw and use vector diagrams, given bearing information, combine vectors and given algebra, find resultant vectors, so result of combining vectors. Okay, so linking back to what they've done previously then, this we're starting off with. I've used mini whiteboards here. 8 minus 6 and label it B. Think of another direction that can move A to B. 8 minus 6. Okay, so 8 minus 6 would be, we'll see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. That would be there. So the aim of this, okay, so they've got a column vector. They've probably not even thought about why they've called it a vector here. But another way of expressing this, you can refer back, maybe, okay, if we say from north, we could measure that and give a bearing and a distance as well. Okay, the thing to bear in mind that 8 minus 6, that's that bearing, isn't it? That's the column vector, beg your pardon. 8 minus 6. We can take that vector, that particular column vector, it moves 8 across to the right in the positive x direction and 6 in the negative y direction. We can move that around. If I can ungroup this, let's see if we can work this out. So I take that vector now. Okay, the arrow's gone, but you get the idea. It doesn't matter if it's moving A or it's moving another point over here. Let's call this C. Okay, C to D, also 8 minus 6. So what we're seeing is another vector here, the same as our original vector. Well, I say it's the same as our original vector. It is the original vector. Okay, so we've got those two vectors. So on this page, wherever I put this line now, and you assume the arrow is pointing down, right, bottom, top, or left, bottom, right, our vector's the same. I think this equivalence that a vector, represented by, in this case, moving something, isn't it? Okay, or it's displacing A to B, if we want to start using the right words. It could be anywhere on that page. Okay, that would be an 8 minus 6 displacement. This would be an 8 minus 6 displacement. This would be an 8 minus 6 displacement. It doesn't have to have squares in the background there. Okay, and it's probably a good point to mention that I'm going to focus mainly on talking about displacement vectors throughout as a sort of basis to understand what's going on here, because I think that's students can relate to that quite easily. Okay, so a vector then. What makes it a vector? Well, what has it got? It's got the vector has the effect in this case of displacing A to B. It's got a direction, A to B, and it's also got a magnitude or a size. Okay, and 8, 6, if you've got top set, you probably get them to use the Pythagoras for that very quickly to get 10 units from A to B. So, it's got size and it's got direction. If I don't put the arrow in there, we have no direction. We've just got a line. Is it B to A or is it A to B? We need the direction. Okay, so what is a vector? We're talking about these, and it's worth spending a bit of time, I think, talking about scalar and vector quantities. They would have covered this probably in science, but I think some parallel definitions are important here. Speed and velocity, what's the difference? Distance and displacement. Distance of 10 miles, and sometimes I'll walk around the classroom and just use paces, okay? And I treat a certain direction as positive, and I walk in that direction. I say, okay, that's from my original position. If I do 3 paces, I'm plus three strides. Okay. Then if I go backwards by 1 go back to the original position and then move backwards, I'm minus 1 stride. Try and get the idea about displacement. I say, well, what distance have I moved? If I've moved forward 3 and then backwards, then back to the original position, back 1, I've actually moved a distance of 7 units. However, my displacement is still minus 1. So it's getting the idea of what displacement and distance is. And the fact is, distance it has no direction, it just has size. Okay, so once I've covered that, this is really just reminding them what they did in the previous lesson, the bearings lesson. So if you've not watched that, it's probably worth going back to that, because from that we achieved this diagram. Now, they may not all have achieved that diagram. You'll be able to pull these out if you save them. If not, you can always put up on the board. They'll probably recognise it. But it's quite, even if we don't use it in this lesson, the fact that you've got it there, they will go, oh, you see their names on top. Oh, yeah, I remember doing that. Okay, so we will come, and I say we'll come back to this first, but we need to do a little warm-up task, because we're going to do some questions on this using vectors rather than bearings, and see that vectors can replace bearings as a way of describing how an aircraft can move in this example. Okay, so the warm-up task. Well, this was a grid of a crosshatch area, a box, like a box junction thing outside the school. It used to be outside the school, actually. And from that, again, because it was relevant to them, it was in their environment, what I then did is took that diagram. In fact, originally when I did this, I took students out there, but it's not there anymore, so I've got to find something else. But some of them still remember it, so I can still use it for a little while longer, but I will replace it. And then what we've got, all I've done is taken those letters on that grid. And I've said about, how do we actually go about analysing this then? So I said, well, vectors, like we've just said, have size and direction. So this vector can get me from O to A here. Okay, we can talk about a displacement vector here. We could call that a column vector. That could be column vector, could be 2, 2. Okay, so we could say that O to A is 2, 2. But it's now getting over the point that actually what we can do is we can just we can give that vector a letter. And again, underline the vector to emphasize that when we write vectors, we put them in bold. We're not going to do that on pages, are we? Because we do that if we're going to push through the page, so we underline. Although I do forgive them for missing it off at this stage. Okay, so O to A is A. Is A, okay, and OM is B. So we're doing a bit of practice on mini whiteboards here about trying to work things out here. So I've got a sheet for them to work on in a minute, but we do some of these together to get started with, okay? So if OA takes me from O to A, how do I get from O to B? I need 2 of the same vectors added together. So I'm not explicitly talking about nose to tail here, addition of vectors. but we're going in the same direction. So it makes sense. We've got an A plus another A, so we're going to get A plus A, and like algebra, this can be combined to give us 2A. Okay. So we do a bit of practice with this as well, getting the hang of using these vectors. Now, A to O, on the money whiteboard when I first started, I'd keep it very basic, A to O, O to M, M to O. Okay, all these displacement vectors. If I was standing at M, what vector would I use to get me displaced to O? Well, that'd be negative B, because it's in the opposite direction. So we're starting to bring in the direction element of this as well. And they do have common misconceptions. Sometimes they think that because it's the same length, we can they get that idea that a vector like this one, AD, for example, AD, sometimes they'll come out and say, oh, look, it's minus A or negative A. Well, I'm not sure why that comes out, but it does come out that way. So what we can start doing then is if we're looking at something a bit more complicated, OD, for example, we can say, well, OD, we can get A plus AD. Now, AD is the same as OL. We can get OL because it is parallel, has the same direction, same magnitude. So OL is 2B, and so is AD. And then, I'll ask them, write me a vector which is the same as AD on your mini whiteboards. Give me an example of a vector that's the same as OB. So we start to reinforce that vector can appear anywhere on the page, but we can also use it. It's got equivalent vectors all over this diagram. So that's the warm-up activity. And then from there, once they've got the hang of that, this is algebraic now, and we said, reinforce this. This will displace them around this particular grid. Once they've done that, we give them something there to work on. So we sort of work with that one together and mark that this is an independent task. And it's slightly out of order here. I then refer back to what we did in the bearings lesson. So I take this diagram, I remove the map, and now I've got a vector diagram. Now, there's a lot of information on this. So this is more for higher students. With foundation students, I probably, unless somebody's really pushing, I wouldn't be putting them on this. I would probably get them to reinforce their understanding by doing these questions and maybe using a textbook examples to back that up, and then going on to column vectors. I'll probably go then on to column vectors, which I'm going to talk about in a second. But if you're doing higher, you can use the map, remove it. You've got a vector diagram, and I devise some questions for these as well. So again, instead of saying red, amber, green, I'll just give it a different name. So if you're advanced, now you will get students who jump in at this. You probably do need to work through this. And you can see what it's covering there. It covers this sort of ratio problem. I like to bring those in. And when I'm teaching that, if CL to CS, for example, 1 to 9, I say, well, put numbers on your line, 1 to 9. So how many parts is that altogether? Well, all of that to be 10 parts altogether. Okay, we've got 10 parts altogether, which means CL is 1/9 of CS, and LS is 9. Sorry, 1/9, 1/10. Sorry, me saying split to 10, then I didn't even do it, did I? And LS is 9/10 of CS, or any other sort of fraction. But it helps you get the fraction there, which sometimes causes the problem. Well, often causes the problem with this sort of question. Okay, so there's problems there, and they're pretty challenging. They'll keep them going. So the final part, and again, both foundation and higher will need to cover this, is column vectors, working with the column vectors. So we're going back again to column vectors. We've worked with algebra, going back to the same diagram. And as I said before, I could call this 2, 2. Okay, so from translation, we could say that OA or vector A is 2, 2. And B then, well, it's half of it, isn't it? So it's going to be 1, negative 1. So we start looking at how do we do that? OB then, what would OB be? Well, we know that's A plus A. What's that in column vector language? That's 2, 2 plus 2, 2. Obviously, it might obviously make that step and say, oh yeah, well, that's 4, 4. It's great because you can actually show them what's going on here, okay? So you've got another one, saying 2, 2. So overall, how far horizontally have we moved from O? We've moved a 2 and a 2, and moved 2 and 2, so it becomes 4 horizontally and 4 vertically. So it validates this method here, okay? When they get to situations where they have to subtract vectors, I think I've shown an example over here. So this is the sheet I give in the end. Again, quite welcome to use this. There's no worksheet for this. You'd obviously have to screenshot this and use it in that way. I can clear off this in a minute, actually, if that helps. A plus B, that's good, adding there. A plus 3C, or 2C, A subtract B. And what I'd ask them to do here is with these column vectors, they can do it anywhere on the page, and they should know this is a great way for them to see that the vectors can be represented anywhere on the page. Draw them, and then they find the resultant. And you see, I've said that's the resultant, which makes sense, doesn't it? A result of adding 2 vectors here. So the resultant I've shown in purple here, which is 5, 1. Okay, it's not the neatest diagram, but you get the idea. This was actually used in a lesson here. So what I wanted them to do is draw them and see that that result made sense when they did this. 3C, I mean, subtracting vectors I was on about first, wasn't I? A subtract B would have been 2, negative 1, subtract 3, 2. I think with that one, it's not too bad. You've got 2 subtract 3 is negative 1, and negative 1 subtract 2 is negative 3. That's probably not too bad, that one there. There can be problems with signs when we end up with situations where we're subtracting negatives, and you can have to use the sign conventions, obviously, with those as you go along. This particular one, A plus 3C, we've got A plus 3C. You know, what do you do here? Well, if I had something like this, I'd write it like this first. As we've got here, 2 minus 1 plus 3 lots of minus 1, negative 3. 2, negative 1. I would multiply this one. I wouldn't try and do it all in one go here. So we say plus, keep the positive in there because it makes sense. You need to find that easier. 3 times negative 1 is negative 3, and 3 times negative 3 is negative 9. What does that actually mean, 3C, as well? It's a good idea to talk about what 3C means. 3C means 3 lots of vector C. So, minus 1, minus 3, 3 times. Minus 1, minus 3. Minus 1, minus 3. I just did plus 1, plus minus 3. Let's try again. Right, let's go again. So, minus 1, minus 3. Minus 1, minus 3, minus 1, minus 3. And if we join the resultant of those, you will end up with what you're after, minus 3, minus 9. And we can see that quite clearly. So there's our resultant vector. 1, 2, 3, and then all the way down there. Excuse my writing here. Trying the best on one of these pads. Okay, I think that's all we've got. I mean, follow up then with this, as usual, I would give an idea of what sort of thing they could be asking in assessment. That's a bit more of a challenging one. It's got ratio in there, but you can get these from Exam Wizard or whatever board you use. There will be some, or past papers. So I have, chosen a selection of these then to assess them. And you'll notice a lot of these are just abstract, although there are now more and more coming into the GCSE at this stage in 2020, column vector questions. But weirdly, even some of my students, this shows how how much of a problem I think vectors is at GCSE. A lot of my foundation students get this question correct without me even teaching vectors. I haven't got to that stage by the time the mocks came about, which, you know, it's great for them, but they get something right, but they don't know what they're getting right, which, you know, not a great situation, I don't think. So hopefully this will give context. I hope you found something useful from that, and I will see you next time. Okay, thank you very much for listening.